In this video, I'm going to be giving you an overview of the end-to-end data science process for building a classification model in Python, and I'm going to be catering to both technical and business audiences. Let's dive in. Alright, in this video, I'm going to be doing a breakdown of all the discovery work for a data science project that tries to predict employee churn. I'll be showing lots of code for those who want to brush up on their data science and programming skills, and I'll be talking through lots of visuals as well, especially to help those from our business and non-technical audiences understand the data science process, something I encourage data scientists to practice more of, as data storytelling is one of the most impactful skills that you can have. Now, what I have here is a Jupyter Notebook, which has been the bread and butter for data scientists worldwide for almost a decade now. Now, notebooks, they're great for discovery work, and that's the nature of data science. You want a playpen where you can run snippets of code in isolation from another, where you can try and break things and fail fast. By the way, my name is Cole. I'm an engineer and data scientist at a large Australian bank, and I'm a researcher at a large Australian university, and my goal here is to make great tutorials for working professionals. Now, diving into my notebook. In this top cell, I've given the 30,000 feet view of what I did in this data science project. This is good practice to help any collaborators and stakeholders quickly understand all the work you did. It's also good for yourself if you come back to your notebook in 2 years' time and forgot everything you did. Now, in data science, we almost always start with a business problem. That's where your project funding often comes from when you're working in a company. So for this demo, let's suppose you work for a mid-sized company and your HR department has asked you to build a predictive model that helps them prevent talented employees leaving the company, because replacing employees is generally quite expensive. Right? So that's the business problem with tangible business benefits. In this case, retaining good employees that saves your company a lot of money in the long run. Now, to train my model, I'm going to be given a labeled data set of around 14,000 past and present employees. I actually got this data set from elitedatascience.com a number of years back when I was transitioning from academia to industry and learning data science myself. Now, a few quick words on some important concepts. This data set is labeled, which means our project is diving into what's called supervised learning. And because I'm going to try and predict a categorical variable, in this case, the status of whether an employee will stay in the company or churn, given information about themselves, this is what's called a classification task. In fact, it's going to be a binary classification problem because my target variable that I'm trying to predict only has two labels, i.e. they've either left or they're still employed at the company. By the way, the other type of supervised learning task is called regression. That's when your target variable, which is what you're trying to predict, is a numerical variable, an example being house prices. We'll dive into regression in another video. Finally, what are we going to be delivering to our HR department at the end of all of this, right? Because that's where your effort, your hard work will actually have real impact and real value. Well, we're going to deliver three things. Number one, a pickle file, which is essentially our winning trained model, a couple of handy Python scripts that HR can run to process new data and make all the new features that I end up engineering for the model. And finally, a list of feature importances. And this is immediately going to give HR insights on the kind of factors that might send employees over the edge and make them want to leave the company. These are insights your business stakeholders can use without ever using your machine learning model to score any new data. So we're going to deliver these three things. All right, let's march forth, shall we? The first thing data scientists do is what's called exploratory data analysis, EDA. This is where you get your hands dirty. You dive into the data to get a feel of it, understand its structure, spot some of the issues, and this is going to help you work out how you need to clean the data for your machine learning algorithms, and also getting some ideas on what kind of extra features you might want to engineer and feed into your model to train an even better performing model. So what does all that look like? Well, Here I'm going to load some important Python libraries to get us on our way, such as pandas for data manipulation. Right? This allows you to put your data into things called data frames, which are basically like supercharged Excel tables that lives in your Python code. Pandas stands for panel data. You've got NumPy for numerical computing, right, which enables you to do things like linear algebra, operations between matrices, and so on. NumPy stands for numerical Python. You've got Matplotlib and Seaborn. These are your standard libraries for making visualizations with Python. And you've got scikit-learn, Python's go-to library for machine learning. All right, with these key libraries loaded, I'm now going to read my dataset and save it as a pandas data frame and begin exploring what my data looks like. So here we can see the first 10 rows, and for each row we have information about a particular employee, specifically the number of hours they work each month, the number of projects they're currently working on, so both of these are proxies for measuring workload. You've got which department they worked in, we've got whether they've filed a complaint in the last 3 years, and also satisfaction. So both of these are proxies for measuring employee happiness. Notice the nans here, by the way, that's missing data that we'll need to deal with later. You've also got their last employee evaluation score, right? Performance reviews from their boss, and also whether they were promoted in the last 3 years. So both of these are proxies for measuring employee performance. You've also got salary, how much money they earn, and you've got tenure, the number of years they've been at the company. This is a proxy for, I guess, experience. And finally, you've got status. So this is our target variable, and it's labeled because we're told whether the employee is still here or they've left. And our goal, of course, is to build a good machine learning model that can accurately predict these labels. Now, all this information about the columns of the dataset should be available to you in what's called a data dictionary. So when you work with data in a company, you have access to data dictionaries that explain in business terms what all the attributes and columns mean in a given table. Now, hopefully you'll also get access to the table's data lineage as well, right? This tells you a story, often visually, of where your data came from, all the way back from how it was created at the source, along with its journey to where it is today, right? So data lineage is very important, especially when it comes to finding root causes for data quality issues. All right, so summarizing our data set, we have a total of 10 columns telling us a variety of information on over 14,000 past and present employees, where they work in the company, how much money they earn, how hard they work, how experienced they are they a performer, are they happy? And based on all this information, are they currently still employed or have they called it quits? Now, in terms of categorical features versus numerical features, we only have 3 features that are categorical. For example, department, where the classes are sales, support, engineering, IT, and so on, the various departments of the company. But the majority of our variables, 7 of them, are numerical, which means their values are going to be numbers. For example, the average monthly hours they work, last evaluation, end projects, which is the number of projects that they've worked on, and so on. These are all numerical features. So, without further ado, let's dive into our 7 numerical features first. I'm going to write some code to get some basic statistics and histograms to try and understand their distributions. Now, the goal here is to get a feel of these features, get to know the quirks, and see where there might be some interesting outliers. For instance, if we look at average monthly hours, I've got a bimodal distribution with 2 peaks. All right, fair enough, because some people work part-time and some people work full-time. Interestingly, for performance evaluations, we have a bimodal distribution as well. Lots of employees getting average reviews from their boss, but also a lot of employees who are being rated as top performers as well. Job satisfaction, right? A good number of employees reporting pretty low job satisfaction. And hey, I wouldn't be surprised if a lot of these people weren't around anymore. On tenure, right, many employees called it quits after the 3-year mark. Is that normal for this industry? Maybe, maybe not. This is where a data scientist might infuse some of their domain knowledge to bring in further insights. Finally, note that these histograms are at the moment kind of useless for certain features like filed complaint and recently promoted. Because unlike the other numerical features, these two features currently only have one value because it's either NaN, basically missing data, or the value 1, right? Making these features currently useless to graph in a histogram at the moment. We'll have to clean up these NaNs later on. Now, my suspicion is that these two features are meant to be indicator variables, where one indicates some condition, like yes, this employee has filed a complaint, or yes, this employee has been promoted. And if it's not one, it means that the employee hasn't lodged a complaint or been promoted. Next up, correlation heat map. Now, this handsome looking graph basically tells you how correlated every numerical feature is to every other numerical feature, right? And the main reason we care so much about this is often we don't want to feed highly correlated features into our machine learning models. This can cause problems like overfitting, right? A classic problem where your model learns all the noise from the training data and can't generalize on new unseen data very well, right? For certain linear models like linear regression, logistic regression, you can also end up with what's called unstable coefficients, right? Which makes your model results less reliable. So here, from this heat map, we can actually see that we don't really have multicollinearity, right? In other words, we don't really have any highly correlated pairs of features, right? None of these boxes in the heat map, apart from this diagonal here, show any correlation coefficients close to 1 or -1, which is good. All right, now let's dive into our 3 categorical features. So we've got department, which has 12 classes. Lots of employees in engineering, support, and sales. Now, do we actually have 12 departments in the company? And the answer is not quite, right? Because we can see one department here that's kind of being duplicated across 2 classes. IT and information technology, right? This is the same department. So here we'll make a note to clean up that later. And this is an example of a data quality issue, specifically a data consistency issue. Next up, we've got salary with 3 classes, low, medium, and high. The majority of employees earn a low and medium income, we can see here. And finally, we've got our target variable, status, which has 2 classes, employed and left, with roughly 75% being employed and a minority 25% left. So this is called an imbalanced dataset, where a majority class dominates the model's predictions, which means you're going to be careful which metrics you're going to use to evaluate your machine learning model later on. Thankfully, our dataset isn't terribly imbalanced. Some common examples of really imbalanced datasets include healthcare, right? Datasets for detecting diseases, finance, datasets for detecting fraudulent transactions, also manufacturing, datasets for detecting machine failures. All right, finally, I want to mention that our ML algorithms like to chew on numbers, not text. So later on during data cleaning, we're going to be converting these 3 categorical features into numerical form using things like dummy variables and label encoding. This is something you generally have to do when preparing your categorical features for your models. It's a standard part of data pre-processing that data scientists need to do. We can also do some aggregations on our categorical features. If I want to see how employee workload varies across the different departments in the company, I can group my data by the department using a group by, which is a staple technique used by data analysts to aggregate data. You might have seen a lot of group bys if you use SQL. So here I find that the engineering department puts in the most monthly hours, but look, the differences between departments aren't terribly big. Interestingly, temporary workers only clock about 100 hours a month on average. That's around 22 hours a week. And this makes sense. This actually makes sense, right? If we go back to our histogram earlier, we can now, I guess, say with some confidence that this bump here of part-time workers are actually just the temporary workers and contractors at the company, and that if you're a permanent employee, chances are, hey, you are probably working full-time. Now, We can also do some segmentations, really cool stuff. This is a way to combine categorical and numerical features together to drill deeper into your data. Now, what I've done is segment a series of 5 numerical features: satisfaction, last evaluation, average monthly hours, the number of projects, and tenure by our target variable status, and plotted the data on some what are called violin plots. Now, the reason these segmentations are interesting is because I'm trying to predict the labels for status, right? Whether an employee is still at the company or have left. So seeing how important factors like how happy the employees are, how they're performing, how hard they work, how long they've been at the company, seeing how these factors relate to employee churn, whether they're still here or they've left, that gives me some good insight on what may be some of the key drivers for employee churn. By the way, these violin plots are made using Seaborn. They're an upgrade to the vanilla box plots that you can do with Matplotlib, where in addition to the summary statistics you get from a box plot, you also get to see your data's distribution and its density. All right, so let's quickly talk through our 5 violin plots. So starting from the top, looking at into the relationship between happiness and whether they're still around, we can see that employees who weren't terribly happy, reporting a satisfaction of 5 out of 10 or less, often ended up leaving. And those who reported healthier satisfaction numbers had lower amounts of churn. Fair enough, not too many surprises there, I think. Now, looking at performance versus churn, this one's interesting. Both high performers, so those with a high last evaluation rating from their boss, and the average performers, right? Those with their last evaluations being around 5 out of 10. That group had a large amount of churn. Very interesting. So there are probably some other important factors beyond competency that determines whether employees decided to stay or not. All right, looking at workload versus churn, there's a large amount of churn for those who are juggling a lower amount of projects. All right, that's very interesting, but there could be good reasons for this. Off the top of my head, maybe there's a lot of churn for the temporary workers who happen to get less projects simply because they were part-time, right? So something we might want to look into. And if you're an HR or organizational behavior expert, maybe you've got some insights of your own already. Feel free to share those in the comments below. Finally, let's check out experience versus churn, and we can see that people started leaving the company at around the 3-year mark at pretty substantial numbers. And if you want, you might even want to drill in deeper and see how this plays out from department to department, right? Maybe our engineers are churning faster than our salespeople and so on. Things like this would be great insights for our HR department. All right, so to sum up, we did 5 univariate segmentations where we plotted one numerical feature at a time against a categorical variable. And I thought there were 3 particularly interesting observations that I do want to investigate further. Number 1, employees who left were often quite satisfied in their roles. Number 2, employees who left often had a low workload. And number 3, employees who left were often the company's best performers, right? A fact that HR would certainly not want to hear for sure. So what I'll do now is investigate further by doing some bivariate segmentations. I'm going to plot 2 numerical features at a time against status, which is our target variable, and that's going to give us some even richer insights on our data. All right, so in the first plot here, I want to look at employee happiness and performance at the same time. So I've plotted satisfaction and last evaluation together. The dots represent individual employees, either those who have left, they're the dots in blue, and those who are still here, which are the dots in orange. Now, because I'm interested in factors that contribute to employee churn, and this plot is right now just a bit too messy with everything on it at once, I'm going to remove the orange dots, right? I'm going to remove the employees who are still at the company, which leaves me with just the churned employees, those who have called it quits. And very interesting, we can immediately see an interesting picture form with 3 clusters of employees who tend to churn. employees reporting low satisfaction but have a high last evaluation. Employees reporting okay satisfaction but have low last evaluation. And the folks who have both high satisfaction and high last evaluation. Now, putting this another way, you've basically got a group of unhappy employees who have probably checked out mentally. Now, this is called employee disengagement. It's a known phenomenon. You've got the underperformers, right? I'll call them that. Perhaps the incompetent employees, that's part of that group. And you've got what I'll call the overachievers, right? They're happy and they perform well, yet they still left the company. Very interesting. So 3 personas there that has a clear relationship with employee churn. Next up, we can look at performance and workload together, right? By plotting last evaluation and average monthly hours together. And again, we see some distinct clustering going on. We see what I like to call a slackers cluster, those who don't work much and have low performance reviews. We see a stars cluster, right? Highly competent employees who also work high hours, over 60 hours a week for many of these folks. So very interesting. Maybe the slackers have high churn because, well, maybe they were fired, right? I don't know. My data set doesn't tell me whether employees left on their own volition or they were given the sack. That's something that we might want to clarify from HR. And the stars, who perform well, work long hours, they left. Not terribly surprising. Maybe some of these folks felt like their efforts weren't being properly rewarded. There wasn't career progression. They weren't being paid enough, right? All good insights for HR if any of these are true. Finally, let's look at happiness and workload together by plotting last evaluation and average monthly hours. And we again see some distinct clusters that's going to offer some insights, right? You have what I'll call an overworked cluster of employees, right? These are employees who clock up almost a whopping up to 70 hours a week, right? They have a 70-hour work week, some of these folks, and they rated their work satisfaction pretty low. No surprises there, right? They're probably chronically burnt out day in and day out, right? We also have what I'll call the just a job cluster. These are basically part-timers with average satisfaction, probably just getting by, right? With a decent dose of employee disengagement. And then you've got what I'll call the workaholics, right? Those who consistently clock in between 50 to 60 hours a week, but they're loving it, right? Their work is their life, it seems. So all up, the distinct clusters that showed up in our bivariate segmentations have enabled us to identify 8 employee personas, right, who have a propensity to churn. These are the underperformers, the unhappy crowd, the overachievers, the company stars, the slackers, the workaholics, the just a job group, and then finally the overworked and burnt out gang. I'll call them that. So some great insights there. And later on, we're actually going to build these personas into our data set in the form of new features when we do our feature engineering. All right, we've wrapped up our exploratory data analysis. Now, I will say be mindful of how much time you spend doing EDA. It really can feel like a never-ending hole, but often you'll have deadlines to deliver something. So it's a good idea to time box the amount of time you spend exploring your data. And once you have a good intuitive feel of your data sets, its quirks and problems, what kind of features you might want to engineer, it is time to move on and start processing your data, cleaning it into a form that's ready for your machine learning algorithms. Now, that generally means removing anything that's not really needed, removing things that might impede the ability of your model to learn the signal from the noise. It means dealing with incorrect and missing data, and making sure that categorical variables are transformed into numbers. We'll talk more about that shortly. Also notice that I've called this step data pre-processing discovery, because we're going to write a lot of Python code in a semi-structured kind of way to slowly get our original data set cleaned up. Right? The part of the notebook where data scientists try to clean up their data, if you look at a lot of notebooks, it's often quite long and very messy, right? We might try some things, realize it doesn't work very well, and then go another route. Right, so what you're about to see is my notebook that has been cleaned up a bit. This is a YouTube video after all. I don't want to bore you with a 4-hour live coding session. I don't want to bore you to death. This notebook has been cleaned a bit. But at the end of this tutorial, when we talk about deployment and delivery, you'll see that I package all of our data cleaning steps below, which has already been cleaned a bit, into something really nice, tidy and small and concise for HR to use. Cool, let's dive in. So the first thing I'll do is drop the duplicate rows. They don't add any value, so that cuts down our data set by about 30 rows. Now in a real world setting, duplicate data can be a little bit tricky to deal with. Right? The bank that I work at, we bought out another bank a little while ago. In fact, we have a history of mergers over the last few decades. And because we have several data warehouses running side by side, the exact same customer can be duplicated across multiple systems, multiple data warehouses that don't talk to each other very easily, right? And this creates data quality issues similar to the data consistency issues we saw earlier. All right, next up, I want to deal with missing data, which is another common data quality problem. Now, a quick line of code tells me that we have 6 features that contain missing data to varying degrees. And hey, by the time we finish our data processing, these should all be 0. See these nans for last, evaluation, and recently promoted? So in computing, nan, right, NaN, stands for not a number. And it basically represents undefined values. Now in data science, nan often manifests essentially as missing data, right, which you need to handle by methods like imputation, right, or straight up removal. In this situation, as a data scientist, you might have a chat with HR and ask about these nans, the nature of these nans, why they're there. Maybe there's a good explanation. Now, a likely explanation is that these nans simply means no. This employee didn't file a complaint. No, this employee didn't get promoted, right? Because for things like filing complaints, it tends to make sense that you'd flag something like this only if it happens, right? Because that's when it becomes important. No one cares if you didn't file a complaint. Everyone cares if you do. So with that context, right, I've gone and converted all my nans in these 2 features to zeros, meaning no. Now the next thing I'm going to work on is called label encoding. So this is where we grab a categorical variable, right? For example, salary, which has 3 classes, low, medium, high, and we're going to convert them into numerical labels. So here I've mapped low to 0, medium to 1, and finally high salary to 2. And we do this for several reasons. So first, some algorithms like linear and logistic regression, they can't work directly with categorical data. For example, the algorithms might need to do some mathematical operations to calculate things like distances and gradients, and it needs numbers for that. Thirdly, interpretability, right? An algorithm doesn't know that low, medium, and high is actually an ordering, right? But numbers like 0, 1, and 2 make that order apparent. It makes it explicit. And this essentially enriches the meaning of this feature for our algorithms. Okay, the next thing I'm going to do is remake my correlation heat map, which is going to bring up all my numerical features and try and identify any multicollinearity for the last time. Right, and we're going to try and get rid of any features that are highly correlated with another one, because again, this can mess with our algorithms. Now notice that this time around, everything's filled in. We don't have any empty rows or columns because we cleaned up some missing data earlier. And there's also an extra column now for salary, right? Extra row and column for salary, because we're now expressing salary, which was originally a categorical variable. We now have a numerical version of that feature. Low, medium, high salaries corresponding to 0, 1, and 2. But still, I see no highly correlated features. So all good. We're going to be able to keep all our numerical features for the modeling. Also, now that I've verified that salary in numerical form, it isn't strongly correlated with any of the other numerical variables. What I'm actually going to do is, and you don't have to do this, but what I'm actually going to do is delete this feature, even though I just built it, and go back to the original categorical version of salary, just because later on, you're going to see I'm going to bring up this nice convenient Python function called getDummies, which will be able to convert all my categorical features, like salary and like department, into numerical features in one swell swoop with a single line of code. Really nice. All right, the next thing I'm going to do is some general cleaning on the department feature. Now here's what it currently looks like. We've got 12 classes. I'm going to combine IT and information technology, right? These two classes, I'm going to combine them together because they are the same department. We identified this issue earlier during our exploratory data analysis. So now we've got 11 classes. It looks better. I'm then going to remove the temp employees from our data set, right? These are our temporary and contractor workers. I'm removing them because generally talent retention is something that HR departments tend to do for the company's permanent employees, right? By definition, temp workers are just temporary. Another thing is temps and contractors, they sometimes operate with a different mindset, like slightly different mindset, because they know they're only going to be here for a certain amount of time. And without going into too much detail on organizational behavioral psychology, this might actually be noise for the model we're trying to create. So let's get rid of temp. All right, so the department feature now looks like this after dropping the temp class. We dropped about 150 employees from our data set. Right, we have just 10 classes left, but there is now a one-to-one mapping between classes and departments, right? Actual departments, which is what we want to see. Another interesting thing is that after dropping the temporary workers, all the missing data from the satisfaction and tenure features actually disappeared, right? Which is great news for us. We don't have to deal with that anymore. So maybe from a company processes perspective, it looks like here, the temporary workers and contractors weren't asked about their satisfaction, right? Hence missing data. And maybe their tenure just wasn't recorded for whatever reason, right? Hence missing data. And look, if that's true, I'm not sure I agree with some of these policies, especially not recording down satisfaction. I think it's useful data to look after all your employees. And hey, this could be a suggestion you raise with management. Anyway, we still have two features with missing data left. Department, we've got 709 employees whose department in which they belong, we don't know. And we've also got 1,351 employees, over 1,000 employees with no record of their last evaluation, right? Basically no performance reviews from their boss, with their boss to look at. So what do we do about this? Now, suppose we go talk to HR, and by now, hopefully you realize there's a lot of ongoing conversation between a data scientist and their business stakeholders. So here, the data scientist, hypothetically myself, or perhaps you, if you're doing this tutorial, with who you're delivering for, the HR department of this company. A lot of conversations, a lot of back and forth. Suppose we talk to HR, and for whatever reason, we just can't get that data, right? So maybe these were really old employees where the department data just wasn't captured. Right, maybe it was recorded and then the company restructured so that their old departments no longer exists. And so some of that data was deleted. And for last evaluation, maybe these old employees, managers, used some old paper process that didn't end up being archived by HR digitally, and that data became lost, right? Who knows? The point is, if this data is truly missing, right, as a data scientist, you're either going to want to impute it with another value, and this has its own pros and cons, or at the very least, you want to tell your algorithm that the data is missing. Don't leave it as just nan, right? Telling the algorithm that, hey, this data is missing is meaningful on its own, and that's what we're going to do here. So for our department feature, which is a categorical feature, what I'm going to do is simply replace the nans with a new class called missing. Right, which means we're explicitly telling our model, we're going to be telling our model that we don't know which department these employees came from, but we've lumped them all together as its own class. And for last evaluation, which is a numerical feature, I'm going to create a new indicator variable to indicate missingness. And then I'll replace all the nans in the original column with zeros so that our algorithms will be happy. Great. Now we can see that there's no more missing data. Fantastic. The final thing we need to do is make sure that all our categorical variables are appropriately transformed into numbers, right? For our target variable, status, that means I'm going to encode our two classes, right? Left and employed into numerical labels. So that left is going to become the number 1 and employed is going to become 0. And for our two other categorical features, I'm going to do what's called one-hot encoding on them. Now this basically means creating a dummy variable, also known as an indicator variable, for every class in those features. And that's how I convert all my categorical data into the numerical form that I need for the algorithms. So for department, I have 11 classes, 10 departments plus the one missing category, right? The one missing class. After one hot encoding, I'm going to have 11 new columns, one for each class. For salary, I have 3 classes, low salary, medium salary, high salary. And after one hot encoding, I'm going to have 3 extra columns corresponding to those classes. The great news is one hot encoding is very easy to do in Python. I can just use pandas getDummies function. I can feed in the categorical features I want to one hot encode, which is going to be department and salary here, and voila, it's done. We now have a dummy or indicator variable indicating to us when an employee is in a particular department and when they're in a particular salary band. Really cool, really easy. Finally, note that the getDummies function deletes our original categorical features because well, we can't feed them into the algorithms, so we don't need them. We don't want them there. Great. With our whole data set cleaned, all categorical features now represented in numerical form through dummy or indicator variables, we now have what's called an analytical base table, right? This is a clean, prepared data set that's now ready for our machine learning algorithms to munch on, right? We've grabbed the original data set and we've made it edible for our ML models. So for posterity, let's save a copy of this cooked and prepared data set as a CSV. Cool. All right, we've explored the data. We've then cleaned the data, leveraging the NumPy, Pandas, Matplotlib, and Seaborn Python libraries. We're now ready to do some modeling using the scikit-learn library, which stands for Scientific Kit for Learning. It's Python's go-to open source library for machine learning. But hey, what about feature engineering? Didn't we identify some great ideas for new features, those 8 personas? Well, what I'm actually going to do is 2 rounds of modeling. Right, the first round, I'm going to see how well the model can learn from just our clean data sets alone. Right. We're going to evaluate the results, and then we're going to build those 8 new features we identified earlier into our data set, retrain the model again, and see how much of a performance boost we can squeeze out from our feature engineering. I hope that sounds good. All right, so let's dive into some modeling. The first thing I'm going to do is split my data set into a training set and a test set. And the usual standard is an 80-20 split. So here, for our HR data set, we're going to end up with around 11,000 rows to train our model and almost 3,000 rows to evaluate the performance of that trained model. The next thing I'm going to do is set up what are called scikit-learn pipelines. Now, this gives me a way to streamline my workflow, particularly when I want to try a few different types of algorithms. So pipelines, that allows me to set everything up and run it in an organized way. For this project, to keep things simple, I'm going to try 3 of the most common types of algorithms for classification tasks. Logistic regression, random forest, gradient boosted trees. And you can check out my blog for deep dives into each of these algorithms. Now, in a nutshell, logistic regression tries to draw a boundary to separate the 2 classes of your target variable. Now, to avoid what's called overfitting, which is when your data learns all the nuances and noise from your data and becomes bad at generalizing new data, you can penalize your logistic regression model when it starts veering towards being too complicated during training. This is called regularization. We're going to use 2 types of regularizations. L1, otherwise known as lasso regularization, and another one called L2 or ridge regularization. Now L1, what that does is it tends to make some features completely irrelevant by shrinking their coefficients down to 0, while L2 keeps all the features but reduces their influence. We also need to set some hyperparameters for each of these models before we start training. Now hyperparameters, if you haven't heard of them before, they set the overall strategy for how the model learns. So for example, deciding how big a step the model should take while learning, right, that's called the learning rate. How many times to go through the data, that's called the number of epochs, another hyperparameter. Number of trees, the depth of a decision tree, and so on. Most models tend to have its own suite of hyperparameters that you need to set and tune. For logistic regression models, the type of regularization you want, L1, L2, or others like ElasticNet, these are actually hyperparameters for the logistic regression model. You're telling the model how you want it to penalize complexity, right? And that's something you need to set up before the training starts. All right, now how do we pick the values of these hyperparameters then? It kind of sounds like a bit of a dark art, and yeah, it kind of is. A standard practice is to identify some hyperparameters that matter with each type of model, and then choose a range of values for them that you think makes sense. Now the training process is going to go through all the different combinations of your chosen hyperparameter values in what's called a grid search. Now, as you gain more experience as a data scientist with these algorithms, you're going to get a better understanding of what these hyperparameters mean, how they affect training, and then you'll develop an intuition for choosing hyperparameter values. But ultimately, it is a bit of a dark art. All right, moving on. We've split our data set into training and test sets. We've picked our algorithms that we want to train. We've chosen some hyperparameters to kick us off. And now we're ready to start training these models. We're ready to fit these models to our data set. We're going to teach these models to recognize patterns in our prepared data, right? What we're ultimately doing is getting each model to learn what are called their model parameters. Each algorithm, logistic regression, random forest, gradient boosted trees that we're using, they're going to come with their own bunch of model parameters that the model is going to learn during the training process, which you can kind of think of as knobs and dials, right? As we train each model by feeding it data, the model is going to automatically adjust these knobs and dials to find the best values so that the model can make accurate predictions, right? That's the aim of our machine learning. Now, don't get model parameters confused with hyperparameters. That's one thing I want to call out. Model parameters are what the model learns during training, while hyperparameters are the settings that we choose to guide the learning process, and we set values for these before the training actually starts. Now, the final thing I want to call out is we fitted our model and tuned our hyperparameters with what's called 10-fold cross-validation, right? That's what this Gridsearch CV function with this CV equals 10 argument does. What this means is during the model fitting, the training set itself is actually split up into a further smaller data sets called folds, 10 of them to be exact, for 10 folds validation, cross-validation. And for each fold, we train the model on 9 folds and then validate the results on the remaining 1 fold. And for each model, we end up doing this 10 times. For each hyperparameter combination, I should say, for each model, we end up doing this 10 times until all the folds have had a turn being the validation set. Right, the validation set is also known as the holdout set. So in a nutshell, for each hyperparameter combination, we actually train the model 10 times. And the reason we often use this, what's called K-folds cross-validation technique, is that it often helps us tune our hyperparameters better, and it helps the model generalize better and prevent overfitting. All right, we've done the first round of testing. Fantastic. It's now time to evaluate and assess the performance of our trained models. Now, just to recap, for each of our models, so that's our logistic regression with both L1 and L2 regularization, our random forest, our gradient boosted trees, we've now tuned their parameters, and these models have learnt their model parameters. So that means we've got the winner for each type of model, right? We have a winner L1 regularized logistic regression model. We have a winner L2 regularized logistic regression model. We have a winning random forest model, right? We have a winning gradient boosted tree. We've got the top dogs for every model type. And what we now want to do is look at their performance numbers. And that means looking at their cross-validated performance, but most importantly, their test set performance. And ultimately, our goal is to identify the winning model overall, because that's going to be the model we deliver to our business stakeholders, right? Our HR department, if we wrap up the project without any further retraining. Okay, cross-validated performance. So without going into too much detail, cross-validated performance, that looks at the average accuracy of each model across the 10 folds for our winning hyperparameters. Now, what we're really interested in is our test set performance, right? That is, how well did these winning models perform on our test set, which is 20% of our entire data set we specifically set aside to evaluate our trained models. Now, for classification tasks, there are a variety of metrics that we can use to measure performance, and they each have their pros and cons, right? And they're all calculated from what's called the confusion matrix, which is kind of like a report card that tells you how many times the model got things right? Either true positives or true negatives, and how many times it messed up, right? False positives and false negatives. Now, we're going to look at 5 of the most common types of classification metrics, which is then calculated based on the numbers in our confusion matrix. We're going to look at accuracy, precision, recall, the F1 score, and the area under the ROC curve. ROC stands for Receiver Operator Characteristic. Check out a blog article I wrote that explains all of these metrics in detail. I'll link that in the descriptions down below. Now, in a nutshell, accuracy, that measures how many times the model got it right out of all its attempts, right? It's simple, but it can be misleading for imbalanced data sets. Precision, that tells you the fraction of positive predictions that the model got right. And you use precision when you want to minimize false positives, also known as type 1 errors. So for example, a 40% precision for a spam filter model means that out of all the emails that the model labeled as spam, only 40% of those was actually spam. Now, this wouldn't be great because you don't want important emails to be sent to the spam box. That's very, very bad. So here, false positives are extra bad, right? So spam filter models, they are an example of what's called a high precision model, where false positives really are meant to be minimized. Next up, recall. So this tells you the fraction of actual positives, right? Actual positive predictions that the model got right. And you use recall when you want to minimize not false positives, but false negatives, also known as type 2 errors. So for example, a 40% recall for a COVID test means that the test was only able to detect 40% of positive cases. This wouldn't be great because you don't want to tell people who are actually sick that they're healthy, right? These days, COVID, not the end of the world, but imagine if this was a cancer test, right? A cancer screening test, right? So for these sorts of tests, you really want to avoid false negatives as much as possible here. So good medical tests try to be what are called high recall models, right? Where false negatives are really meant to be minimized. All right, next up, the F1 score. That's a balance between precision and recall. So it's good for minimizing both false positives and false negatives. But the score's a bit more abstract to interpret and understand. And finally, there's the Receiver Operator Characteristic Curve, ROC curve, which isn't the easiest thing to understand, right? Turns out every point on this curve actually corresponds to a certain confusion matrix. See my blog for details, and there are some great YouTube videos out there exploring how this works. The key bit we're interested in is the area under this ROC curve. And this ends up being a great metric that measures how well the model can draw out the signal from the noise. An area of 1 basically means that it's a perfect model. 0.9 is outstanding. And as you go down and get close to 0.5, that's when you're really getting into the mud. It means your model's predictive powers is essentially no better than random guessing. RIP. So coming back to our employee churn modeling, if we compare the numbers between the logistic regressions, the random forest, and the gradient boosted trees that we trained, it was the random forest that performed the best, right? With the gradient boosted trees coming a fairly close second. We can see in the confusion matrix that out of the 2,814 employees in our test set, The model correctly identified 2,132 employees who stayed and 626 who left. And it only made 9 false positives, right? Predicting 9 people have left when they actually stayed. And it only made 47 false negatives, predicting 47 people staying when in actual fact they had left. Now we can calculate our metrics. So for accuracy, our model correctly predicted whether an employee would stay or leave 98% of the time. Precision, when our model predicted that an employee would leave, it was correct around 98.5% of the time. Recall, our model correctly identified 93% of employees who had left. The F1 score of 0.95, that's quite terrific. 1 is perfect and anything above 0.9 is outstanding. Finally, area under the ROC curve. Right, this was a fantastic 99%. The model can almost perfectly distinguish between employees who leave and stayed. Fantastic. Cool, so that's our first training run. The random forest took the cake, edged out the gradient boosted trees, and performed quite a bit better than our logistic regression models, it turns out. In fact, both our decision tree models performed so well that I would say that we could wrap things up now if we wanted to save the trained model as a pickle file, send it over to our HR department, call it a day. Proud of a job well done. Time to pop out the beers. It's time to start the weekend. But remember those great ideas we had for new features from our exploratory data analysis, right? We identified 8 distinct employee personas who were prone to churning. It will be a missed opportunity not to see if we could squeeze out just a little bit extra performance out of our models by engineering those features into our data set and then feeding in some even richer data for our models to munch on. So that's what we'll do now. So let's create these 8 features, 1 for each persona, and we're going to end up with 8 new columns for our data set. Okay, so from our happiness versus performance plot, we identified clusters of unhappy, underperforming, and overachieving employees. We can create features that capture these personas. From our workload versus performance plot, we identified the slackers and the stars of the company. Let's imbrue these personas into our data set as features as well. And finally, from the workload versus happiness plot, we can build features for the workaholics, the just a job employees, and our overworked and burnt out employees. And also notice how we've built these 8 features as indicator variables, right? Flagging any employee who falls under any of these personas with a 1 and 0 otherwise. All right, we can now save the latest version of our analytical base table. This is the latest data set for modeling, which includes all of our original data processing, plus our 8 new features. And we can now retrain our model. And if we do that and look at the results, the random forest, it still takes the cake, right? The area under the ROC curve has increased by just a smidge. But I want to note that our gradient boosted tree is now performing a smidge worse. Very interesting. So it looks like including these new features has actually caused the boosted trees to overtrain just a little bit. What I really want to call out and highlight is that our logistic regression models are now performing a lot better. Right, check out the performance between the old and new models. Area under ROC has jumped from 85% to an outstanding 94%. And if we look at recall, the model can now correctly identify 83% of churn employees, when the last time round it could only manage a 36%. That's a huge difference. But in the end, the logistic regressions improvements, it doesn't really matter for our delivery to HR because our winning model is still the random forest by a long shot. But hey, if you wanted to handicap yourself and all you had to play around with was a logistic regression model for this project, then engineering these features was absolutely a worthwhile endeavor that essentially promoted some average models from competent to excellent, right? That's the power of feature engineering, enriching your data. All right, scrolling down further, these are just the same plots. I just prettied them up a bit for the Medium article that I wrote about this project. Cool. Moving on to the final evaluation phase. So here I've explicitly identified my winning model. in my notebook. I've jotted down the winning hyperparameters. I've got everything I need to retrain the model right here and reproduce my winning metric scores. Now, why am I doing this? Well, just like how you might skim the conclusions of research papers to quickly get the punchline, here at the end of my notebook, I've anchored my winning model, so to speak, the model that matters, right? The model that I'm going to be delivering to HR. It's going to be convenient for me if I need to revisit my discovery work, and it's going to be convenient for any of my stakeholders trying to make sense of what I did and quickly work out my results if they happen to get a copy of this notebook. Now, I will make the comment that if you're working at a large company and you're using enterprise-grade all-in-one machine learning platforms like Dataiku or Microsoft Azure Machine Learning like I am, there will be some built-in features, quality of life features, like versioning control for models that help you track all of your experiments, what were the best scores, which model was the best one, and so forth really easily. But for small-scale projects where everything is pretty much in a notebook, organizing a few things before putting it into storage, for me, it has always been worthwhile. Also, in this part of the notebook, right, in this final evaluation part, I also like to write some code to print out a chart of ranked feature importances. Now, remember, this is something we promised the HR department, right? It's one of our 3 deliverables alongside our trained model and any scripts needed for them to process their data. So this is me playing with some code to try and work out how to do it and also make it look pretty. And here is the result. I then played a bit more to massage the graph, the plot into something that's slightly more readable with the bars and text all going horizontally. So this diagram provides a ranking of our features. I'm going to be careful with my language here, based on their relative contribution to the model's predictions. Now at the top, we see that the number of projects, which is a proxy for workload, that has the greatest relative impact on the model's decisions. Satisfaction and tenure, essentially how happy the employee is, how long they've been at the company, those features follow as close second and third as most important. Going down the list, we can see some of the extra personas we engineered make the cut, like our stars, overworked persona, slackers, overachievers, workaholics. It's great to see. So this list is going to be useful information for HR to sink their teeth into and help them craft new policies, refine any targeted strategies to retain employees. Now let's briefly talk about the limitations of feature importances, and there are 2 things I really want to stress. Number 1, causation. So feature importances, they don't imply causation. Right? So be very careful not to overstate the significance of feature importances to your business stakeholders, in this case to HR. Number 2, feature importances, right? This chart, it doesn't show the direction or the nature of these relationships. So for example, I can't tell from this plot alone that more projects, right, i.e. a higher workload, means higher chances of churn. Maybe it's the other way around. Maybe it's that less projects means a higher chance of churn. Right? In some enterprise software that I've used, you do get this information, which is nice, but not in this chart here. So be very careful. So if you want to be technically correct, you can say to HR, if you show them this graph, right, as part of your deliverables, that features like the number of projects, satisfaction, and tenure is strongly related to employee churn. And that compared to the other features in the model, our model relies on these features significantly to make decisions. If the values of these most important features change, that means that it can lead to big changes in the likelihood of the model predicting churn, right? Sounds like a little bit like a politician's speech here, but you do have to be quite careful with how you interpret your results. You don't want to misconstrue them. You don't want to overstate them. All right, finally, deployment and delivery, which is actually where the value of your work really comes to life by having people start using your model to score new data, right? Now, what does deployment generally look like in a data science process? So for smaller projects on smaller data sets, this might mean that you email your business stakeholders, your trained model, and you also email them any supporting files that they need to begin using it. And that's basically it, right? For the larger projects with big data, so now we're going from one end of the spectrum to the other, right? Where you might need your model to begin scoring new data in real time that's fed via an API to an app that millions of people need to access 24/7. This is where things get more complicated because you're going to need to call in some cavalry, some engineering cavalry to help you complete the job. And that's likely going to include your company's data engineering team, right? To help you build some enterprise grade data plumbing that's going to feed data into your model. And you're going to need machine learning engineers to grab your Python scripts and turn them into performant and bug-free code that's then going to be deployed in a production IT environment where it can then serve customers 24/7. It's going to be accessible via APIs. It's going to be monitored for things like data and model drift and so on, right? This is called ML Ops. It stands for Machine Learning Operations. Check out my recent article on the evolution of data science, where we are today, where I talk about all of these different roles. Now, since our data set is small, only 14,000 rows, this isn't a big data problem, right? We don't need data engineers to build any data pipelines for us. And if HR is happy to run the model themselves on a need to score basis, we don't really need to involve the tech department either. There's no need to deploy this model into some sort of production environment that's babysat by an IT team. This really is a fairly small scale data science project where the data scientists can complete the project end to end. Right, we just need to deliver to HR two things: a final pickle file, which is our winning model, and also the code that they would need to run on new unseen data on their own laptops to massage and process that new data into the form needed for the model, right? And for that, I've written two cells here. The first one packages all of the data cleaning steps we prototyped out earlier during our discovery work into a nice and tidy function. And the second cell neatly creates those 8 extra features we engineered into a nice and tidy function. So whenever HR needs to score new data, they would first run 2 simple Python functions on their new data to instantly clean it and build in our engineered features. And then they run that prepared data through our pickle file, which is then going to score their data and make predictions, right? Whether any future employee is likely going to churn or likely going to stay. All right, that's it for this tutorial. We covered a lot of stuff. Please hit the like button if you found this end-to-end walkthrough for building a simple binary classification model useful. If you have any comments or feedback, please drop a comment. I'd love to hear from you. Also, check out my blog. I publish a ton of data science and enterprise data content there. In fact, this demo today is based on a project I did a few years back and wrote about back then, right? Again, shout out to Elite Data Science for the dataset and their fantastic data science training resources. All right, keep learning and growing, guys. Enjoy the process, and I'll see you in the next video. Have a good one.